Thank you, Sarah. It's really nice to be here, and thank you for the invitation. So I'll talk about some work that we're currently wrapping up with Mingyang Deng, who is an undergrad at MIT, and Jonathan Tidor, who is my recent PhD student, who's now at Stanford. So it's about uniform sets with few progressions. So when we first learn the basics of basic theorems in additive combinatorics, one of the first things we encounter is the proof of Ross theorem. And one of the important ideas in the proof of Ross theorem is that Fourier uniformity implies that the number of 3APs is close to what you would expect in a random set of the same density. Okay. So let me write down this a little bit more precisely. So if you have A, a subset of Z mod n, and if you have some bound on all the non-zero Fourier coefficients, then it implies that the 3AP count, 3AP density is close to what you expect in a random set. So this is a standard notation for 3AP density in A. Now, the next thing you might learn in this, well, once you see the proof of Ross theorem, then you ask, well, what about for four-term arithmetic progressions? And then you'll be taught that this proof doesn't quite work for four-term arithmetic progressions. And the basic reason there is that Fourier uniformity does not imply that the number of 4APs is close to random. And there's a standard counterexample that is usually given. And the example basically is taking the set of all elements X whose square mod n lies in some interval.
So can I ask a very basic question? Really basic. What is alpha?
So alpha is the density of A. Alpha n is the number of elements. Thank you. So please ask questions. Okay, great. So alpha, think of alpha as some constant. So this is a set that one can do some basic calculations and essentially through Gauss sums find that it is Fourier uniform, in the sense that the Fourier coefficients are all small. Okay, so it's Fourier uniform, so the number of 3APs is close to random. But the number of 4APs actually is quite large. And the reason is that whenever you have a 3AP, the following identity so there's this base, so this is just an algebraic identity. So if the first three terms lie in some interval, it is quite correlated that the fourth one will have a good chance of also lying in that interval. So the 4AP density is roughly the same as the 3AP density. 4AP. So 4AP density up to some constant factor will be around 3AP density, which we saw earlier is around alpha cubed. And that's much larger than what you would expect in a random set, which is alpha to the fourth. Okay, fine. So because of this reason, the standard proof of Ross theorem via Fourier analysis doesn't quite work. But if you think about it a little bit further, well, in the proof of Ross theorem, we're using this thing called the density increment argument. And the fact that this set has a lot more 4APs than that of a random set actually is not a problem. Like, you don't mind that there are more 4APs. You only are concerned if there are fewer than random Fourier-APs. So in a way, while this is indeed problematic for the usual proof strategy, this counterexample is maybe somewhat ingenuous, right? So it's maybe not the best example to illustrate why this strategy is necessarily doomed to fail. So the question this motivates is, can a Fourier-uniform set have much less than random Fourier-P? And so we know it can have much larger than random Fourier-P density. What about the other direction, which is the direction that matters for the proof strategy of density increment? For example, if it is the case that a Fourier uniform A always has Fourier-P density at least, let's say, alpha to the 1000, then the proof strategy of Roth's theorem basically works. You can use the same proof strategy and it's fine. There's nothing wrong with it. Now, we do not know if this is true. Right? So the point of this talk is to think about this question, to tell you, what we do know about this question and some related problems that we managed to consider. And okay, so let me state things a bit more precisely. There's a bit of a history to this problem, and it's a little bit, we're actually a little bit confused about what the history is. But basically, Gowers, in his famous paper, where he gave a new proof of Similarities theorem, he wrote in the paper a conjecture that Fourier-uniform sets should always have Fourier-P density at least that of a random set. So that's what he wrote initially. But this was overly ambitious because he later found a counterexample. Basically, with density 4 plus some tiny constant. Okay. And there is some document that lists a bunch of open problems in additive combinatorics.
Last constant of the constant is negative, but
small constant. Yeah, so it's less than random. So so that's the goal. We want to construct Fourier-uniform sets with Fourier-P density less than random. This is less than random. It's not much less than random, but it is less than random. Okay. Yeah, so there's this document that lists, I think it was at some AIM workshop, that lists a long list of open problems in additive combinatorics. And in it, Ruzsa basically reiterates this question and asks, is it the case that for every constant, we can get a bound which is less than, basically, is it possible to exhibit Fourier-uniform sets whose Fourier-P density goes to 0 faster than any polynomial in alpha? So this is still open. So we don't know the answer to this question.
The Roth theorem, you need it to be polynomial, or is it okay if it's another constant?
Good question. So we know just from Similarities theorem that this is at least some function of alpha, which comes out of Similarities theorem, but that function is worse than polynomial. Yeah, so there's. So
that's for any set, not just for you.
For any, that's right. So that requires no assumptions of Fourier uniform, just from the density of A alone.
But to carry out the Roth proof, does it have to be polynomial?
Well, not necessarily. You get some bound if you have some. Yeah. So the one bound translates into another bound.
there is a paper of complement to a paper by Bourgain, where he gives the proof that it cannot be the correct number, but he does it in terms which is hard to interpret.
Okay, I'm not familiar with that.
He has a proof of growth, which is different from ergodic proof, different from, you know, trigonometric sums proof, with curious bounds. It's Bourgainian proof with some estimates of some convolutions. And he ends up with an interesting bound, but it's like often with Bourgain hard to interpret, but it's worth looking.
Okay, so just to clarify, this is a question, right? So we don't know the answer to it. So this is a question and it's still open. So let me just give a definition which captures what we're asking. For every alpha, let rho sub 4 of alpha to be the largest number such that for every epsilon there exists an eta and not such that for every margin of n, bigger than n naught, every eta Fourier-uniform subset A of z mod n with size at least n alpha has for a p density at least rho sub 4 of alpha minus epsilon. Okay, so that's a bit of a mouthful, but basically it's a definition saying what is the best number that you can put here. So that's what we're trying to investigate. And Ruzsa asked this as a question. I don't think, at least in what is written, he doesn't express a view either way. But for our purpose, let me say as a conjecture. I'll say a conjecture rho that for every c, rho sub 4 of alpha is less than alpha to the c for all sufficiently small alpha. We think that it should go to 0 faster than any polynomial. Okay, so that's a conjecture. Now, this is not really the main point of the talk, but let me just tell you some numerical bounds, like what do we currently know. So if you extract what Gowers managed to prove, he gets alpha to the, if you work out what the bound he gets, it's roughly 4 plus some tiny constant, which is 2 times 10 to the minus 8. And then this was somewhat improved by Wolf, who got it to 4 plus some other tiny number, which is around 10 to the minus 6. And we were able to improve this to 4.4. No, this is not really the main point.
So is the answer to Ruzsa's question known for longer progressions?
Yes, so but okay, let me say that until the end, but the short version is that for Fourier uniformity, you can get sets with very few 5 AP density. But the right question is, if you have a higher uniformity control on A, can you say something about longer progressions? And that's an analogous question, so I'll say a bit about that at the end. Great question. All right. So let me now talk about what seems to be a different question that has to do with coloring. So this is an arithmetic Ramsey problem. Let me define a notion of a symmetrically colored 4AP. Okay, this is what it sounds like. It's a 4AP. Where the first and the last term have the same color. And the middle 2 terms have the same color. So essentially a color pattern that's A, B, B, A. It's okay if A and B are the same color. So it's symmetrically colored 4AP. Here is a conjecture that we came up with. Let me call this conjecture C, C for coloring, that there exists a coloring using n to the little 1 colors of the numbers 1 through n that avoids symmetrically colored Fourier piece. Conjecture, so that you can color 1 through n using relatively few colors and to avoid all the color patterns like this. Just to get some benchmark to get you some intuition about what this is. Let me offer a few remarks. One is that, well, one thing you might want to do is to try random coloring. And actually, this is a really nice exercise in the low-vast local lemma. I gave it as a qualifying exam question at one point. So if you try out using local lemma, what you get is that there exists a on the order of root n coloring by the low-vast local lemma. So you can think of that as the benchmark. Now, we don't know whether this conjecture is true, but let me offer some evidence that this is maybe not so easy. Because in such a coloring, every color class must necessarily be free of monochromatic Fourier piece. Okay, so certainly you must have that. So each color class should be quite large, right? And I mean, the size is n to the 1 minus root over 1. And really the only ways that I know of constructing large Fourier free sets is by the Baron construction or some variant of the Baron construction. And those constructions are really bad at avoiding these patterns. So each color class is Fourier free. But Baron, okay, so at a very high level, what the Baron construction is you go to high dimensions and you color using level sets of spheres. And if you color using level sets of spheres, you're going to get a lot of symmetrically colored Fourier piece. That's just like that's the nature of this coloring. Right, so this is really bad for avoiding that type of patterns. Okay. Now, why do we introduce this conjecture? So one of the results in our work is that if this conjecture C is true, then conjecture rho is true.
I have a question.
Yeah.
Did you check what, or if you allow eta to depend on n also, like, right? So if you have like 1 over square root n or whatever uniform, so do you understand the dependence in eta that would make Ruzsa's conjecture maybe?
That I haven't thought about. Yeah, so I think I stated the quantifiers in the right.
Yeah, you stated it correctly.
Right. Yeah.
You stated it correctly. I'm asking if you have any insight on the dependence on. You think Ruzsa's conjecture is false, so I'm asking whether you have some intuition of.
No, I think this conjecture is true. I believe. Well, I believe this conjecture. I mean, Ruzsa asked the question, right? But I believe this conjecture is true. Yeah, I don't know.
Okay.
I'm not sure. So that's one of the things that we prove. Right, so this coloring conjecture implies this one. And let me also offer some evidence that, I mean, we don't know how to prove a converse, but let me show you something that looks like a converse. That it would be, I think, if one proves this conjecture, either the proof technique or whatever, probably you will prove this one as well. So I have some feeling that these two are roughly equivalent, but not formally speaking. But I don't know. So let me say this a bit more quantitatively. So if there exists an R coloring of Z mod NZ, avoiding symmetrically colored Fourier piece, then rho sub 4 of alpha is most. So here I'm really thinking of a specific R and a specific N. If you just exhibit to me one specific coloring, then we can get a bound upper bound on rho of this field. And also by a computer search, we managed to find a 3 coloring of Z mod 22. So one way to do it is using a SAT solver, so you can avoid these colorings, and it exists. And this would lead to, this does lead to rho of alpha less than alpha to the 4. So that's where this difference. There are, so it does seem a little bit strange where up there it's about asymptotic results as n grows, where here this is about a specific R and a specific n. And the reason why they're related to each other is by a tensor power trick. So if you can find a specific coloring, then there is a tensor power trick which allows you to convert a R coloring of Z mod NZ to a R to the L coloring of Z mod N to the L, basically by coloring the digits. And via this connection, the local lemma bound that we saw earlier of n to the 1/2 kind of corresponds to this random bound of alpha, so rho 4 of alpha being at most alpha to the 4. So the local lemma bound up there corresponds to the trivial bound. Okay. Any questions so far? Yeah.
What kind of constraint in this coloring is corresponding to the Fourier-uniform?
Okay, so I'll show you what the construction is. Yeah, so and so are you kind of asking basically how this is proved? No, starting with the coloring. Okay, so maybe
whatever you will say will respond to my questions.
Okay. Yeah, so I mean, I think this, so one reason we like this is that, I mean, the initial question, you know, something about Fourier coefficients, and not everybody likes Fourier coefficients. I think they're nice, but not everybody likes them. But this question, you know, the combinatorialists really like because it's just about coloring 1 through n.
I would argue.
Let me rephrase my
Well, there is
question.
some coloring here. Some people like Fourier and some people don't like it.
Why in this side do you make such a strong assumption, and here you make no assumption at all?
Strong assumption, you mean Fourier uniformity?
Yes.
Okay. Maybe let me show you how that is proved. And so, I mean, there's a reason why it's only implication in one direction. We don't know how to do it the other way. And there's, but maybe ask me that again if, after I say what I'm about to say. So let me explain basically how that theorem is proved, and along the way, let me say why we think that it's almost like a converse, although maybe that's too much of a claim. So let's talk about constructing Fourier uniform sets. Let's view Fourier piece. And the point here is that there's a general class of constructions I will tell you, and this includes all the known constructions, including from previous work. Now, this is not all the constructions, but seems to be a fairly general class of constructions. And the idea is to you first fix some function from the torus. So this is z squared to 0, 1, and let's assume that everything we're working with is Riemann integrable. And for every n, we define function f sub n to be a function on z mod nz, defined by setting value at little n to be evaluating big F at little n over big M squared. So this is kind of related to some standard ideas involving quadratic Fourier analysis. And if we suppose furthermore that f has constant first marginal alpha, meaning that if integrate out the y variable, it's always equal to alpha for almost every x, then by some standard calculations, basically involving biological distribution, one can show that the sequence, now they're functions, but you can convert them to sets. The sequence of functions is Fourier-uniform. With density alpha. As well, I guess that goes to infinity. And furthermore, the Fourier P density converges to some quantity I'll call lambda tilde sub 4 of f. And what this is to evaluate capital F at 4 points, multiply them together. These 4 points are chosen with some relation. And the relation is that the x variables form a 4-term arithmetic progression. And the y variables satisfy this equation. y1 minus 3y2 plus 3y3 minus y4. So f is some function on the torus. Let me draw the torus as a square. So it's some function, and let's imagine it's like a 0, 1 function. And it has constant first marginals. So each vertical line integrates to the same number. And this quantity here is saying that if you sample 4 points, are subject to the condition that the x-axis is Fourier P and the y-axis is symmetric, then, well, not just symmetric, but satisfies some relation like that, then so the y satisfies this single linear equation. What is the product of the values evaluated at these points? Okay, so again, I mean, the proof is a pretty standard calculation involving equidistribution. So let me not go into that. And these are, in some ways, pretty standard ideas in quadratic Fourier analysis. And all the previous constructions, such as the ones up there, are of this form. And this is a pretty good way to construct functions that satisfy, for our purpose. So let me define a new quantity, rho tilde sub 4 of alpha, to be basically what is the answer to the original question if you only allow constructions of this form for some f. So take the infimum over all Riemann integrable f with first marginal with constant first marginal alpha. Okay, so if you only allow these kind of constructions, what should answer to Ruzsa's question be? So let me call this quantity rho tilde sub 4 of alpha. One direction should be clear, is that rho sub 4 is at most rho sub 4 of tilde, because one of them is a special case of the other. And you can let me also make a conjecture, which we'll call rho tilde, which is that for every C rho tilde sub 4 of alpha is less than alpha to the C for O sufficiently small alpha. This goes to 0 faster than any polynomial. So that's also conjecture on a similar theme that we can make. And what we prove is that conjecture rho tilde is equivalent to conjecture C, this coloring conjecture. So that if you restrict your construction to constructions of this very general type, then that question is equivalent to this coloring problem that we do not know how to solve. Yeah.
Question in conjecture rho and rho tilde. The function is of a particular type, is like only 0 and 1s.
Yeah, so I'm being, yeah, so there's a standard thing in arithmetic combinatorics where we don't care that much between 0, 1 value versus interval value.
Some kind of dense term.
Yeah, so I'm kind of glossing over that part. So if you like, initially you can think about interval valued functions, or you can restrict to sets.
I was just a little bit confused because on one hand, one is more general than other.
Yeah, so I would ignore the difference between 0, 1 interval versus 0, 1 set. So that's not that big difference.
You just use the probabilistic construction to get a set out of it? Or are
Exactly.
you putting the functions into your linear?
That's one way to do it. Yeah, so if it helps to clear the confusion, imagine that we're more consistent across the two boards and used maybe 0, 1 set over here. I think that would solve this confusion. But it turns out to be equivalent because of this probabilistic construction. Great. Any more questions? Okay, so these are the main things I want to present, and I guess my main goal is to advertise these questions, and specifically this conjecture about the existence of a coloring avoiding for symmetrically colored Fourier keys. Okay. So in the rest of the talk, I'll sketch some proofs, how to prove these implications. And also towards the end, I'll mention what happens when you talk about longer progressions or different kinds of patterns.
Conjecture C, is it entirely due to you?
We came up with it. Yeah. So in trying to solve this problem, we arrived at a different problem that we didn't know how to solve. Okay, great. All right. So let me sketch how to derive this implication from conjecture C to conjecture rho tilde. So basically it says if you have a good coloring, so suppose there exists an R coloring phi of Z naught and Z, avoiding symmetrically colored Fourier keys. And with R pretty small, so let's say R is n to the little 1. Okay, so here's how we're going to construct this function f. So first, there's a small lemma which says that there exists, so this is a variant of existence of C down set, but easier. So there exists a subset of 1 through n of size roughly square root. Avoiding non-trivial solutions to the equation a minus 3b plus 3c minus d equal to 0. Okay. So just the existence of a subset avoiding the solution to a particular equation. And I'll just tell you what the construction is. You can take all numbers in space 9. Uses digits 0, 1, 2. Okay, so this is pretty easy. Let me not say more. Just think about why this is true. Okay, so that's the end of the proof. So let me take a subset S1 through SR of R is R coloring, a subset of M where M is roughly on the order of R squared, avoiding solutions to this equation. And I want to construct basically a subset of the torus that have the desirable properties, namely that it has constant first marginal alpha, and also that its 4AP, this lambda 4 tilde is small. And the construction basically is going to be the F is, okay, I'm going to represent F by some black and white diagrams. So black means 1, or rather white. So when I color in is 1, and when I don't color in is 0. But first, let me just draw a grid for a visual aid. So I'm going to divide M vertically into, divide this torus into M equal intervals vertically, and N intervals horizontally of the same length. And whenever okay, so then I label the horizontal intervals 1 through N, and at the ith interval, I'm going to look at what is the value of S sub phi of I. So phi was the coloring, right? So I colored 1 through N. I look at what is the coloring of I, and then I look at what is the number I chose here in this set. So that's S sub phi of I. And that corresponds to the ith vertical cell. And I just put in a small, let's say 1/10 of the cell like that. I put that. And I do this, you know, for each, and so on. That's the construction. Okay, so that's the construction. So the reason that this construction has constant first marginals, well, I hope that is clear. So all the vertical lines integrate to the same number. And also the reason why this quantity, this lambda 4 tilde quantity is small, basically is that you are avoiding solutions to this equation. So when you try to do that quantity there, you're not going to get many hits. That's the basic idea. And the converse direction conjecture rho tilde implies conjecture C. So here we start with some F, and I want to extract a coloring that avoids symmetrically colored Fourier-APs. And the way I'm going to extract this coloring is I first sample a random, uniformly chosen random length n AP, and call it x1 through xn. And then I'm also going to sample uniformly independent random vertical entries, vertical coordinates. Okay, so and there's going to be R of them. So y1 through yr, they are uniform and independent on the torus. And the color we're going to define R coloring of 1 through n, and phi of I is going to be the smallest j, such that f xi yj is at least, say, alpha over 2. And if no such j exists, then you consider this construction a failure and you start again. It's the probabilistic construction. Okay. Yeah. So for each number here, to figure out its color, I go through y1, y2, y3 until I find the first one where the value of f there is somewhat large, and I pick the index of y as my color for this number. Okay, so that's the how to extract the coloring from f. And so then one needs to check that this coloring avoids symmetrically colored Fourier piece. And the point is that if it had any symmetrically colored Fourier piece, then the existence of that symmetrically colored Fourier piece would tell you, right, so if you have some Fourier piece that's symmetrically colored, so let me be somewhat okay, so let me just say this. There's a calculation involving the Cauchy-Schwarz inequalities and whatnot, but roughly speaking, if you have patterns like that, then it would indicate to you a lot of solutions to that equation there. So it would provide you a lot of densities to this pattern over here. Yeah, just from if with high probability you got some symmetry colored Fourier piece. So that's roughly how this implication goes. Any questions? So in the last part of the talk, let me explain what happens when you try to generalize this whole story to longer arithmetic progressions or other patterns. So longer patterns. Well, one question you can ask, which I think is the right question, is that is it the case that a set that's Gowers uniformity has u k to the k minus 2 uniform set can it have few k APs? So do there exist uniform sets with few APs, and then I want Gowers uniformity? So the things we just discussed corresponds to k equals to 4. And then U2 uniformity is the same as Fourier uniformity. Okay, so we know now that the answer is yes for R K. As in, if you define this, if you look at the A with, so there exists constructions of A where this KP density decreases like that of the bearing construction, faster than any polynomial. For even k, that's where things get interesting, and we don't know what the answer is, but we were able to show that this question, the whole story generalizes, except the coloring question now is, do there exist n to the little one colorings of 1 to n, avoiding symmetrically colored k APs. So symmetrically colored k AP for k even is what you think it is. So coloring is symmetric back and forth. And now note that if this conjecture is true, conjecture C is true, if you can avoid symmetrically colored 4 APs, then that automatically avoids symmetrically colored 6 APs, and likewise longer APs. So if that conjecture is true, then this is true as well, and that would also imply what happens for longer k, for even k. And finally, what about instead of an evenly spaced arithmetic progression, what if you allow other spacing? So let me start with some constants, a1 through ak, some distinct integers, and define notion of AAP to be generalization of KAP, where I specify some non-uniform spacing. And so as the same story, and what we know is that the answer to this conjecture is yes, if either K is odd or the spectre A is not symmetric. So being symmetric means that the means, if you go from outside in, the pairwise averages are all the same. Okay, so if either of these two happen, then somehow the situation is somewhat easy. And so the more interesting case is if K is even and A is symmetric, then the situation corresponds to a similar story, whether there exists a coloring with few colors of 1 through n, avoiding symmetrically colored AAPs. Okay, so there's more involved technically in these proofs, but the rough idea is along the lines of what I presented. Okay, and that's all.
Yeah, questions.
So can you comment on possible extensions in direction of polynomial progressions?
Ooh, polynomial progressions. We have not thought about that. So guess what you might want to ask is,
One should formulate it better. Suppose I go for progression n square with gaps. It's one game. But suppose I put instead of your difference just quadratic difference, then it will be, I believe, something like what you have, much harder.
You're asking about Ruzsa's question for polynomial progressions or some analog of this question?
Start with what you started with. Your progression is a plus d, a plus 2d.
Right.
You can now make out of these two questions. First of all, a plus d squared.
Okay. Yeah.
That's easier game because of some independence. Right.
Yeah.
And then you can ask a plus d squared, a plus 2d
Oh,
squared.
I see what you're saying.
That's tough.
That is tough. Yeah, I don't know. Yeah, did not think about that. Yes.
Maybe you said this before, but is there any hope to prove that this specific family of constructions is the best possible?
That's a great question. So there are some ideas in coming from quadratic Fourier analysis that tells you that if you have a sequence of constructions, then there might be some limit object that captures that sequence of constructions. And probably the most related thing to this is that you can ask the following question: given a set of density alpha, large n, what is the minimum possible Fourier P density? Can you capture that by some limit object? And so there's some work of Candela-Cizask that characterizes what happens there. But over here, things get somewhat trickier because over so here we fix a single f with constant first marginal alpha. In a limiting sequence, it's not that the first marginals converge to a constant alpha is that they converge to alpha in U2 norm. So we don't know if there is an, it's not necessarily the case that you can always get an F from a sequence of constructions. So, and that's roughly the reason why we don't know a full converse to this conjecture. And it would be nice that we thought we had a full converse, and then we realized that we kind of misunderstood what the Candela-Cizas, Candela-Cizagati paper was about. Is that roughly?
You're saying that the answer would depend on whether this limit exists or not. So, or that's the most natural way to answer it.
Right, and I don't think there's reasons to believe that it should exist in general. But for this specific question, there's no reason to believe that it should exist in general.
So what makes, you said the answer is fully known for odd length progressions.
Yeah.
What makes that easier?
Okay, great. Yeah, so when you no, that's a great question. So when you have odd length progressions, make sure I get the right answer. So blanking out a little bit. I have the answer, but I'm
There are some identities which are better or more convenient for you for odd than for even. You have to fight. You see this identity, that's one of the things you have to deal with. But in odd situation, maybe.
Yeah, okay. No, I have the answer for you, which is that it's about avoiding non-trivial solutions and non-trivial coloring. Okay. In a situation,
Cauchy Schwarz, right? But you can't do that with odd.
okay, so let me try to say something and you can tell me whether this makes sense. Right. So over here, the story is about trying to R-color Z mod NZ, avoiding symmetrically colored Fourier-APs. And the reason why you care about symmetrically colored Fourier-APs is that the kind of trivial solutions to this equation, they involve A equals to D and B equals to C. And that's kind of where the symmetry comes in. But if you have another equation, so what would be the equation for 4? So what are trivial equations for this equation? Actually, they're not so trivial, right? So you don't have trivial equations. And so that obstacle isn't there. So the situation is much easier. Okay, so the idea of a trivial equation to this solution is just like it's not relevant. Great question. Anything else?
I'm going to copy Vitaly and ask, have you thought about multidimensional versions? Like a set that's pseudorandom with respect to like a box norm and the 2 skew box norms that control the count of corners. Like, can it have very few axis line squares?
We have not thought about that, but I would, let me think more about it. But I
feel like that should be not as impossible as like 3 APs with square common difference.
Right. No, I think 3 APs with square common difference is much more difficult. I need to think about that. I don't have an answer. Yes.
If you restrict this function big F more, you want it to be, I don't know, polynomial or some other kind of restricted class of functions.
Yeah.
Do you end up with something interesting, or does it sort of just?
So you want to restrict, so it's big F to be for little f.
Yeah, so you're saying big F is maybe big F is enough to come up with good, like low density for AP sets. So maybe you can restrict big F even more, or maybe you can figure out when it's too restrictive.
Yeah, I mean, already at the level of big F, we know that it's equivalent to this coloring situation.
Yeah.
And so, and we don't really know how to, I mean, maybe the question is analogous to what about some more structured colorings? Yeah, I don't know. I mean, so, and that actually we did think about a little bit, because you can look at Barron's construction and ask, what are other ways you can vary Barron's construction? Barron's construction is somewhat algebraic. Right? So maybe if you look for other algebraic things, well, as soon as you go beyond quadratic, you get pseudo-uniformity, pseudo-randomness that just, it's not going to work. So you have to stick with quadratics, but then you run into this issue. So, yeah, so I think maybe what you're asking is analogous to more algebraically or otherwise structured colorings. And we tried that and wasn't able to get that to work.
You looked at the class of like big F, that's just of the form that you drew, where you take a curve and then you shift it down.
Mm-hmm. What would
take some function Q of X,
yeah,
from 0, 1 to 0, 1, and then that gives you the top curve,
okay,
and then
yeah.
you
I
shift it down. Maybe this would clearly have too many because you'll contain intervals.
Yeah, not how we think about this problem, but yeah, that's interesting. I don't know. We can think about it. Yeah, it doesn't. And I don't quite see what advantage it might have, but I'm not sure.
Any more questions? Questions from Zoom? Okay. If there are no more questions, let's thank Yufei again for a great talk.